Okay, sorry about that. I will start again. I'm going to present this work, which is titled Estimation of Carbon Content and Change in Southern Chile Permanent Forest during the 2010-2015 monitoring period with K-NN and ALOS PALSAR mosaics. This is an ongoing collaboration between CONAF in Chile and some Spanish institutions. And I would like to thank JAXA again for providing the Earth observation data. And I would also like to thank iuFOR for providing the field inventory data. So the context for this work is that there is an increasing need to report on national carbon stocks and the temporal changes, and countries have to report with spatial accuracy. So there is a need of tools and techniques that are adapted to local idiosyncrasies. Each country has different needs. Some countries have the capacity to acquire lots of field data and can provide good statistics with that, other countries cannot. In particular in Chile, Chile commits to report on carbon pools in permanent forests, but not in plantations. And this country requires spatial estimations of carbon at different dates. In particular, they chose to select the 2001-2010 as the reference period for forest emissions, and they have to compare later emissions for any other period to this reference period. So, fortunately, there is remote sensing. There are remote sensing methods or approaches to estimate carbon, and these approaches comply with the IPCC recommendations and requirements for estimation of biomass and carbon with a Tier 3 approach. A Tier 3 approach means that the estimations have spatial reference, that each estimation of carbon or each point on the ground of the forest has an estimation. To provide you some context, Chile has more than 14 million hectares of native forest, so they have to report on this extension. The native forests represent more than 80% of the total land, and the variety of forest types is quite high. There are at least 12 different forest types, but 4 of them make 75% of the forest area. In particular, the southern regions have the most extensive forest and the most diverse forest. But the area is very extensive, the forests are remote, there is no easy access to those forests, and these circumstances preclude acquiring enough field data to make good statistics. In addition to that, the southern area of Chile is covered with clouds. I wouldn't say most of the year, but with a high frequency, which poses an additional challenge for remote sensing approaches based on optical data. So there is a need to look for some kind of data which can see through the clouds for estimations of forest variables. So the goal of the work was to develop and test a Tier 3, that is with spatial reference, Tier 3 methodology for retrospective estimation of carbon pools. Retrospective, think that Sentinel-2 started acquiring data in 2014, and we needed estimations for 2010 and 2015. So we needed to look for a different source of data. So we had to estimate carbon pools based on some kind of SAR data, which had acquired observations prior to Sentinel-2. And we selected, well, we needed to do that in 3 administrative regions of the south of Chile. In Los Lagos, which is the administrative region 10, Aysén, which is number 11, and Magallanes. This is going from north to south. So the only possible source of data to make those estimations with a remote distance approach is ALOS PALSAR, the ALOS PALSAR program. In particular, PALSAR 1 could provide data for reference date 2010, and PALSAR 2 for date 2015. We selected one pilot site in each of these administrative regions. In Los Lagos, CONAF, our Chilean partner, had tried an approach based on optical data, and we wanted to compare our approach and our results with the previous methodology. In Puerto Cisnes, Puerto Cisnes and Bahía Inútil were the two other test or pilot regions, pilot sites in regions Aysén and Magallanes. In total, we had more than 40,000 square kilometers of permanent forest to work with. And going from north to south, the diversity of forest types decreases. So you can see that in the northern region, there are 5 representative forest types, whereas in the most southern region, there are only 2 forest types. So we needed ALOS PALSAR data. We decided to use the 2010 and 2015 25-meter annual mosaics because they are spatially complete. They are free and available. They are acquired with L-band ALOS PALSAR, and they were available in Google Earth Engine. We also worked with another set of ALOS PALSAR data, which is the finding dual dataset, which can be used to do polarimetric methodologies. That is, this dataset has magnitude and phase, and with this dataset, more advanced approaches can be done. We also have some field plots from the continuous field forest inventory provided by iuFOR, and forest maps derived from the cadastral reference data. So this is an example of the ALOS PALSAR mosaic, which was composed of different strips. And to provide you some notions of the other dataset, it's provided in smaller tiles, so the amount of data is much larger with this type of data, and therefore the processing is much more complex. There were some available field measurements in each of the test sites. Going from north to south, the number of plots decreases because the accessibility decreases. So in Bahía Mansa, in region 10, we have this overall distribution of plots, whereas in the southern one, there were less plots available. So the sampling intensity varies per region, but also by forest type. To give you an idea of the distribution of volume measured on the ground, we can observe that for different forest types, the volumetric distribution is different. For example, in the forest type Siempre Verde, this distribution of volumes gives an idea that there is some management of the forest, whereas in other forest types, we can see that there is no management. In fact, Alerce is protected, it's a protected forest type, so there is no management at all after some decades. So this is to provide context for the approach. The data were acquired with some temporal decorrelation. We didn't have data acquired, or the data was not possible to acquire on the same date. So there was going to be the correlation between the acquisitions, which went from 2001 to 2019. And if you recall, our reference dates are 2010 and 2015. So when we build the models, there's going to be some temporal decorrelation. Even though we updated the field data with growth factors to update the volumetric data to the reference dates. So the processing of the data was different for the pulsar mosaics. We followed a standard processing with coefficients provided by JAXA, and calculated some variables which will work as predictive variables. In particular, we used HH and HB polarizations, the ratio among them, and one index which is the RFDI. It's named sometimes radar forest degradation index, but in reality it's a structural index. For the polarimetric approach, in which we used pulsar FBD data acquired in 2007, we followed our standard processing with the goal of making an unsupervised classification, which is named alpha-Wisher dual pole. This classification is based on the dominant method of bus scattering in each pixel, and results in a classification based or a classification by structure. So the result of this polarimetric classification is 9 different levels of complexity in the forest. Okay, so we have the field data acquisitions, we have the Earth observations from the radar sensor, so we were ready to apply the statistical modeling. We decided to select K-NN, regression K-NN, which is a non-parametric approach, because of the scarcity of data, and also because we were only using 4 variables. We didn't want to use, or we deemed not adequate to use any other machine learning approaches like random forest, SVM, or any others. K-NN regression was adequate for this idiosyncrasy, this contingency. So the dependent variable was volume measured on the ground, and the independent variables were these 4 spectral variables. K-NN is a spatially scalable statistical model, and the predictions are based on the similarity of the spectral space. So we were going to use spectral vectors, or spectral dimension, to infer volumetric estimations. Okay, the models were derived and applied individually for each of the 6 dominant forest types. That's why we needed the forest mask from catastrophe. And the uncertainty of the models was evaluated by applying a bootstrapping approach. So we repeated the modeling 100 times and selected a 95% confidence interval. We also tried the transferability of models. We tested it to transfer models between different regions, between different types, and between different dates. All these options of transferability were tested because we wanted to know if with one date of data on the ground, we could model or update our model to any other date. And as outcomes, we had spatial estimations with 25 by 25 meter pixels of a number of variables. First of all, volume for these 2 dates, the reference dates, change in volume, which was just the difference between the two, 2010 and 2015. We derived carbon content for the 2 dates with the standard formula. We evaluated change in carbon content between the 2 dates, the 2 reference dates. We evaluated the equivalent CO2 flux and the annual equivalent CO2 flux. And the last variable that we evaluated was the uncertainty. So we had all those products with a spatial estimation of 25 by 25 meter pixel, and then we calculated also some area statistics. Okay, the results, the models, they varied, and they were more accurate in one type of forest type depending on the region. For example, in Los Lagos, Siempre Verde was the most accurate model, probably because the highest number of plots were placed in Siempre Verde, and in the southern region of Magallanes, there was only one model, a combined model for the 2 forest types, Lenga and Coihue de Magallanes. Overall, the more or most accurate results were obtained when the field and the spectral data were temporally closer. In fact, although I have not mentioned here, there was an additional date for which we made all the models. This additional date was the most recent one for which we had field data, and it was 2019, 2018 and 2017 for each of the regions, and those models were the most accurate. But we were obliged to evaluate carbon content in 2010 and 2015. Okay, this is to give you an idea of the resulting products. This is an example from the intermediate region, which had an intermediate diversity of forest types. Volume was distributed with this pattern. The white areas are masked. The scale was specific for each of the regions. The volumetric scale was specifically designed for each of the regions. We derived the carbon content map, equivalent CO2 flux, and annual CO2 flux. We verified the results of the models in each of the field plots and evaluated relative absolute error and absolute error for each of the forest type in each of the test or pilot sites. In general, the relative absolute errors were moderate, but depending on the forest type, they were lower, where there were more field plots, and the absolute error in the Magallanes region was very low until reaching certain amount of volume, and for the most volumetric plots there was an underestimation. In the other 2 test sites there is a clear overestimation of the lower volumes and a clear underestimation of the higher volumes for all the forest types. Regarding the uncertainty, we evaluated 2 measures: the standard deviation of estimations and the 95% confidence interval. Both measures follow a similar pattern, and we could see that there is a higher uncertainty in steep areas, which is normal because radar data has more difficulties in steep areas. There are some very well-known effects when the area is very steep, because as you know, SAR data beams not vertically but heading on a side. So when there is a steep area, there are some problems for processing data. The graphs down here show that the uncertainty was distributed more regular in 2010, whereas in 2015 there are some peaks of uncertainty in some of the volumetric intervals. And I would like to remark from this methodological approach that to be a retrospective methodology, it was successful because it provided previously inexistent estimations of carbon, complying with a Tier 3 approach, and it was able to work with very few field observations, which is what it is. That's what we have, as Felipe mentioned this morning. Data and overall field data is probably the most valuable thing we have. On the downside, I would say that the temporal decorrelation between field data and Earth observation data led to modeling uncertainties. Well, that makes us think that perhaps when acquiring data in the field, we should do a previous work for stratification, and remote sensing has a lot to do there. So we have to think of the way of planning our field campaigns. And on the good side, on the upside, we found some transferability of models between dates and regions, which is promising to estimate carbon at different dates, because we have a continuous coverage of Earth observation, even though there is no continuous field data. We have Earth observations with continuity. And another good point of the methodology is that it is extensible to at least 80% of the forest area in the southern regions of Chile. So for the future, we are going to evaluate what's the human impact on permanent forest and compare the changes, the level of change in protected and non-protected areas. And our goal is to design a framework for temporal analysis of forest carbon pools with annual models with acquisitions of ALOS PALSAR 2 and ALOS 4 PALSAR 3.